start, let me present the speaker today. Our speaker is Souvik Ghose from Harish-Chandra Research Institute. He's a postdoc there. He got his PhD in 2015 at the University of North Bengal. And he is a specialist in a number of things like theoretical cosmology, dark energy models, and accretion flows onto black holes, and two more things which I cannot write now read. It's darkish. But today the seminar will not be along those lines. So we will hear on the origin of Sagnac. Floor is yours.
Thank you. So, good afternoon, everyone. Thank you, Professor Cheney, for inviting me here and presenting me with this opportunity to present this work in front of you. As she mentioned, this is not my primary research area. A couple of years ago, along with my two seniors, I got interested in the foundational aspects of special relativity, the paradoxes or the apparent paradoxes in special relativity, and we did a work on what is known as Sagnac effect. So in today's lecture, what I try to do is that introduce what is Sagnac effect in special relativity, what was the motivation behind the theory of Sagnac effect, why it was challenging at that time, and how it got incorporated in special relativity. Then there were some recent experiments on Sagnac effect, which led to some problem or inconsistency maybe, and there was a proposed resolution. In fact, this proposed resolution by Tatalia and others is what motivated us to work on this problem. We did not think that the motivation of those work was correct. At least there were some caveats. We tried to sort of resolve the paradox or fit it in a more better way. And this is the topic in the fifth point, the origin of the Sagnac effect, what we think it is behind the Sagnac effect. And finally, I conclude with a few takeaways and the open issues as we see. Yeah. So it goes long back. Newton actually had conceptualized space as something absolute. That is, it exists regardless of presence of any material or anything. This idea was, however, challenged in 1893 by Mach, and later at 1905, Einstein, with his famous discovery of special relativity, abandoned the notion of absolute space as well as the notion of absolute time. STR was, of course, a very successful theory, and it still is. But in 1913, George Sagnac discovered an effect, and his motivation was to bring back the concept of universal ether as the medium of propagation of light in vacuum. So he did an experiment, and he proposed or propagated a theory to explain his experimental results, which seemingly reaffirmed the absolute notion of absolute space, or at least indirectly through the notion of existence of ether as the medium of propagation of light in vacuum. This is the schematic representation of Sagnac's experiment. This D1, D2, D3 are mirrors. C acts as mirror as also a beam splitter. Any light ray that originates at A gets splitted by this C. And one light ray propagates in the clockwise direction, like C, D3, D2, D1, and back to C. The otherwise in the counterclockwise direction, D1, D2, D3, back to C. They eventually meet at B and produce an interference pattern. Now, this entire setup is mounted on a turntable or a disk which can rotate. So it was seen that when the disk itself is set to rotation, that means the entire setup, when it is rotated, and not in relativistic speed, just rotation, there is a fringe shift in the interference pattern. So Sagnac set out to explain why this is occurring. Because in the laboratory frame, since D1, D2, D3, C, etc., retains their relative positions, and if light speed is absolute, like C, there should not be any fringe shift in the observational, the dismounted observer. So this was Sagnac's original apparatus, the spherical representation of Sagnac apparatus. And this is more like the case. So from the laboratory observer, it's quite simple what is happening. Suppose the emitter is at T when the light ray is emitted, and one is propagating counterclockwise, the other is propagating clockwise. The disk rotates the counterclockwise direction in this way. So for the beam which co-rotates, it starts here, goes to the perimeter in a circular loop. But when it is primarily received, by that time the emitter has propagated a certain distance delta L. So it has to travel an additional path of delta L. Whereas for the other beam, which is counter-rotating, it gets emitted here, but it gets received here. It does not have to complete a full cycle. It kind of travels a distance delta L less. So if we put that in the mathematics, if we try to compute the time taken by the light ray, both light rays, after emission and before reception, this T plus, which is the co-rotating, is L plus delta L by C, where L is the length of the perimeter and delta L is that additional distance, which should certainly be equal to delta L by V, where V is the linear velocity, linear speed of the detector, which is R omega. Omega is the rotational speed and R is the radius of the disk. So this will lead to T plus equal to L by C minus V. A similar calculation, if we do for the other beam, it is T minus equal to L plus L by C plus V. So the delay, if we calculate it from the laboratory, is this. In terms of R omega, this becomes this. Up to a leading order, then we get this expression. And this A is just pi r squared, the area of the disk. Why up to leading order? Because eventually we'll not be measuring the time delay, we'll rather be measuring the fringe shift. And it will so happen that whatever we can measure experimentally in fringe shift within reasonable uncertainty, only the leading order terms of these expressions are relevant. We cannot test the theory up to second order even now. In the time of Sagnac, this situation was even more marginal. So this is the phase shift for light of wavelength lambda, which occurs because of this time delay, and which eventually leads to the fringe. Now the problem was how to reconcile this effect from the disk frame. Because if we, for a moment, do not consider rotation as a non-inertial thing and something, the entire setup is moving. There is no change in the relative positions between the mirrors, emitter, and receiver. We are still getting a fringe shift. If light velocity is constant, there should not be any fringe shift, apart from the rotational effect, which will come back. Yes. Sagnac, because he was in favor of the ether theory, he tried to incorporate it by treating light as anything else. So he'll just come up with the relative speed formula, this simple velocity addition. And for the co-rotating beam, it becomes C minus V. The counter-rotating beam, it becomes C plus V. So from the disk frame, the calculation is simple. And it exactly matches the laboratory frame. It in fact explained his experimental data by considering C plus V and C minus V, which certainly we are sure that is not a correct thing to do for light. But nevertheless, he got the correct result. So for him, it was a conclusive proof that there is something like ether through which light propagates, and he was in favor of that. Anyway, So Sagnac, when he performed this experiment in 1904, he performed with it indigo mercury light, a loop area of 866 centimeters square and a rotation rate of 2 rotations per second. And he obtained a shift of 0.07 fringes in terms of fringe, etc. That's how he presented his result. So from an extensive review article of Post, who studied the optical experiments during that era, he concludes that at the time of Sagnac, the fringe shift detectability was probability of the order of 0.01. So Sagnac's result was fairly marginal. As it turns out, that before Sagnac, in 1911, a German PhD student, Harness, did a similar kind of experiment. But his goal was different. So although he had the data, he never made this kind of calculation or talked about any Sagnac-like experiment. But later, someone called Herzer reworked Harris's data and found similar result as obtained by Sagnac. And in fact, it was a better result. I mean, it was done with better precision. In addition, in his experiments, Herzer could also conclude that the result is unaffected by presence of any refracting medium which would co-move with the disk. So if there is a medium, refracting medium, but it co-moves with the disk, the result remains unaffected. Later, in 1925, 26, and 1928, Michelson, Gale, Poniani, and others demonstrated the same effect with greater and greater precision. So all these experiments conclusively proved the following things. Firstly, the observed fringe shift is exactly given by the Sagnac's formula. This is the phase shift formula. It translates to fringe shift. It does not depend on the area A, on the shape of the area A. It does not depend on the location of the center rotation. That means it does not have to be the center of the disk or something. It does not depend on the presence of any co-moving refractive medium in the beam path. Now that at that point of time, it created a problem because certainly the theoretical explanation that light speed is to be velocity added or subtracted, like going to C plus equal to C minus V or C minus equal to C plus V, was not the correct idea. We knew that special relativity was correct. And yet there was no special relativistic treatment of the Sagnac effect available at that time, partly because it was involving rotation, and Lorentz transformation formula do not directly take care of the rotation itself. So that remained, and people say that it would be consistent with special relativity, and probably Sagnac effect is an artifact of the rotation because the frame is becoming non-inertial, so it should be an artifact of that thing. Sagnac effect is a real effect, and it has these present applications in GPAs and many gyroscope building of many gyroscopes. The basic idea is to measure the fringe shift and from that conclude the speed of rotation. So there are lots of applications, but let us concentrate on how to get a treatment of the Sagnac effect, which is consistent with the special theory of relativity. Now, what do we expect? We expect that if we can compute the delays in two frames, in the disk frame and the laboratory frames, they should be, if it is consistent with special theory of relativity, they should be consistent with the time dilation formula. So in 1921, Paul Langevin came up with a method to establish this relation. What he did is that he considered a line element for an inertial observer in polar coordinate, as simple as this. Then he used this following transformation rule, that dt goes to gamma dt, dr goes to dr prime, d theta goes to d theta prime plus gamma omega dt prime. But what Langevin did, he did not consider gamma to be that special relativistic factor. Instead, he chose gamma to be an arbitrary factor, but a factor which does not depend on theta prime. I'm sorry, there is a typo. This is theta prime. So gamma is independent of theta prime. Apart from that, there was no restriction. It was just an arbitrary factor. So the transform line elements now read as this. We are trying to explain Sagnac effect where the light rays move along the perimeter of the disk. So for our case, R prime is equal to R, leading to dr prime equal to 0 and a simplification of the metric. Now this, because we are considering light ray, it should be a null line element, and this gives a quadratic equation in dt prime. So dt prime has two roots like this. Now, the journey times in the disk frame is obtained by integrating theta prime either from 0 to 2 pi or 0 to minus 2 pi, depending on the direction of propagation of the light. And from this 15, we can get two expressions for co-rotating and counter-rotating beams, the time of flight of industry. If we compute the delay, and since we have transformed the matrix, we are computing it for the disk, it comes as this. The gamma factor is there. So certainly, it is something similar to equation 10. Yes, because if we do it in the laboratory frame, this is the part we get. So it is related with the gamma factor. And it was accepted as the proper special relativistic treatment at that time. Until today, if one talks about the special relativistic treatment of Sagnac effect, people talk about the Langevin's method. Now, the equivalence between equation 10, that is that time dilation relation, and equation 17 is preserved for any gamma as long as it does not depend on theta prime. Langevin, in his original work, chose gamma equal to 1, and that reduced the transformation 12 to an absolute Galilean type rotation, d theta equal to this. In which case, the time delay in the laboratory and time delay in the disk are the same. But if we choose gamma to be the special relativistic correction factor, then the laboratory frame delay remains unaltered as expected, but the disk frame delay becomes slightly altered. Here, the fraction arises. But the problem is when we try to test it, both the original expression by Sagnac 5, the 19 and 20, all are practically indistinguishable because we are still measuring the fringe shifts. And even with today's apparatus, we can test the theory only up to the first order. And any correction of journey time due to special relativistic effect, and there are many other effects, there are approaches which consider general relativistic effects also. Any correction comes at the second order. So it is not possible till now to test the theory up to the second order to determine whether that gamma factor actually is there or not, whether our application was correct or not. It seems correct, but there were some caveats. Firstly, if you look at Langevin's method, he considers a metric from the laboratory frame, then transforms it to the rotational frame. So what he is actually doing, he is talking about a metric that a lab-based observer will infer for the observer who is rotating. He is not directly writing down the metric or the line element for the rotating observer. Now, this creates a few problems. For example, Langevin, while taking his transformation, chose a constant radius. R prime was capital R, leading to dr prime equal to 0. The radius was constant. For rotating frame, for a rotating observer, whether the radius will be a constant or not is a debatable issue still. It leads to something called Ehrenfest paradox, that for a rotating observer, the ratio of the perimeter and the radius is not 2 pi, and etc. So it's prone to that paradox. And even if we can explain mathematically the thing, it is not testable yet. So we are not sure whether we have got the correct formula. But anyway, that's the best bet we have. But there were some other recent experiments which created the problem. Till now, even if we accept Langevin treatment to be the legitimate special relativistic treatment of the Sagnac effect, it does not talk about the origin of the Sagnac effect. It is to be understood that the origin of the Sagnac effect is purely rotation. Because of the rotation, something like this is happening. But in 2003, Wang and others performed a series of experiments with moving fiber, what they call fiber optic conveyors. So these are rotating pulleys, and the conveyor, fiber optic conveyor belt is moving here. So they set up a Sagnac-like experiment with all these kinds of configuration, particularly this configuration, which they termed as zero area configuration. And they could single out the contribution from the linearly moving part. The Sagnac delay was obtained from the linearly moving part. It has nothing to do with the rotation. So earlier, we were expecting that Sagnac delay is something which is originating because of the non-inertial nature of the frame, because the frame was rotating. But here, we are getting results from the part which is moving linearly. There is nothing non-inertial about that. So that again raised an issue that what should be the origin of the Sagnac effect then. Later in 2015, Takami et al. Suggested a thought experiment, and they explained the linear origin of Sagnac effect with that thought experiment and propagated a special relativistically consistent theory as well. So this is their setup. They have a rectangular setup. These are the meters, M1, M2, M3, M4. Here, at 0, 0 of the coordinate system, they have initially the emitter as well as the receiver. Once the emitter emits light from 0, 0, it starts moving towards M1. But they have considered velocity to be small enough so that even a beam which is emitted in this direction moves in this direction and gets received somewhere here. The velocity should not be large enough so that before receiving, the emitter crosses this meter. So somewhere between 0, 0 and M1, the emitter will receive both the signals, one propagating in this direction, the other propagating in this direction. They showed that this is completely equivalent, and they get a Sagnac type effect. Okay. So this is for the counterclockwise rotation. This is because these three coordinates are CT at any time CT, anytime X, and Y. So this is the first event, emission 0, 0, 0. The second event, CT is A. Also the reflection occurs at A0, and the Y coordinate is 0, and so on. From here, they could calculate the total time of propagation as CT1 equal to this. Similarly, for a clockwise propagating light, they could calculate the time of flight as C2 T2 equal to this, eventually getting a time difference of this. But because now they are working with a linear system, Lorentz transformation is directly applicable. So they did that. These are the events in the lab frame, and if they calculate, they get back the same delay with the correct gamma factor with it. So they said that it would be the proper special relativistic treatment of the Sagnac effect, and they described, or they concluded about the origin of the Sagnac effect. Two reasons. They talked about two reasons. Firstly, the relative motion between the meters and the emitter. And secondly, if you notice, one light path for the counterclockwise propagating beam is closed. It has an overlapping region because by the time it gets received, the emitter moves a certain distance here. The other part is not closed because it does not have the opportunity to come back to 0, 0. So they suggested that these two are the main reasons behind the Sagnac effect. One is non-closure of the two light paths, and the second is the relative motion between the emitter and the mirror. So this is where we set out to see whether that is actually the case. We considered a generalized version of something called linear Sagnac effect, which was probably first described in 2003 by Ghose et al. How much time do we have?
Like 20 minutes for main presentation. And
yeah, okay. Probably I'll not need that much. So, okay. So Ghose et al. At 2003 proposed a linear equivalent of Sagnac effect. Not as complicated as that earlier, not a rectangular array, just two mirrors. But in their thought experiment, the observer, the emitter, and the receiver were both placed at the same location, as is the case for any Sagnac type experiment. What we did, we generalized the experiment by choosing a detector which is initially at O, emitter initially at O, and the detector initially at Q, a certain distance away from O. Now, after the emission, the detector starts moving towards A. Consequently, it makes two detections at D1 and D2. One light is going here, getting reflected here, the other is going here, getting reflected here.
So this detector is not moving uniformly.
Yeah.
It is accelerated at some moment, right? Because this is what you say. It is first at rest and then accelerates
Just
to
after,
the velocity.
yeah, there is a point of acceleration, right? Exactly. So it emits and then goes on moving. But okay, we can readjust the experiment. For example, we can keep it continuously moving. Once it reaches Q, when it reaches Q, the O can emit the light. We can get rid of acceleration. We can try to get rid of acceleration in that way. So O is practically fixed. Q can go on moving. Once it reaches Q, O emits light. That will get rid of that acceleration. So in the first case, we consider that the detectors start moving with a speed v in the laboratory frame, but so do the mirrors. So the detector moves, but so does the mirror. So relative position between the detector and the mirror does not change. In that case, the observed delay is this. And if you put Q equal to 0, that is, if you put the detector and the emitter at the same position, there will be no time delay, or there will be no Sagnac-like fringe shift, which is expected because it is equivalent to the case when the disk is not rotating. Okay. For a non-zero Q, there is a delay, but that is certainly because the path difference. So it is consistent. Now, in the second case, we allow the detector to move with the speed v, but the mirrors remain stationary in the laboratory frame. Now there is a relative movement between the mirror and the detector, and it can be shown to be the completely equivalent of the four mirror formation described in Tataria et al. And we calculate the delay to be delta t equal to this in the left frame. And since it is a linear thing, we can always just apply the Lorentz transformation and calculate the time delay in the observed frame, and this comes out to be this. Again, the both delays are connected by a simple time dilation. But what we achieve by placing the detector at a particular position Q away from the emitter is that for a certain Q, there will be no Sagnac delay, even in this case, which should be equivalent to the moving mirror or the Tataria's experiment. So if we adjust Q, if it is somewhere around there, there will be no Sagnac delay even in this case.
Pardon?
Yeah.
Could you please remind what was the Q?
Q was this.
Q.
Okay.
Yeah. The shift between the observer and the source.
Yeah. The initial distance between the observer and the emitter.
Thank you.
Yeah. Okay. So we can adjust that distance, and for a particular distance, we'll not get any Sagnac effect, although it is expected to get Sagnac effect there.
For a given L and V, yeah?
Yeah, correct.
So this all has to be
Right.
together.
Right, yes. For a given L and V, we can always have some distance for which there will be no Sagnac delay. There will be no Sagnac effect. So can we do it for the Sagnac type case? We have calculated for the Sagnac type case as well. And we obtain delta TL here and delta TD here. D is the rotating frame time period. And then again, they are related by a gamma factor. And more importantly, we get back the original Sagnac formula when we place P equal to 0. P in this case is the initial separation. This initial separation. So if we get set P equal to 0, that is, we consider the Sagnac type arrangement where the emitter and the detector are placed in the same position, we get back the original Sagnac result. But what it does, it allows us to identify another position P for which even in Sagnac effect experiment, there will be no Sagnac type delay or no fringe shift. Okay, so we try to do the same calculation as Langevin. We considered the same kind of line element, but we considered gamma equal to 1. And we calculated it for our case where there is a finite separation initially between the emitter and the receptor. And we could come up with delta TCL clockwise as this, and delta anticlockwise as this, leading to, again, a fringe shift or a time delay. But even in this case, the important thing is to note that we can always adjust P, we can always find a position for which there will be no Sagnac effect. Now, this is something unexpected, because if it is Sagnac effect is purely due to rotation, or if it is due to the relative motion between the mirror and the observer or the receptor, if it is due to the non-closure of the light path and all, at every position, there should be a Sagnac delay. There should not be a position for which we are not getting any Sagnac delay. So what could be hinting on? We suggest, we propagate that Sagnac effect is basically originating because what seems to be a symmetric placement of the detector in one frame does not remain symmetric in the other frame. For example, if we consider the rectangular setup, the light path, when seen from the detector's frame, are like this. One for the clockwise propagation, this one for counterclockwise propagation. So the detector is, the light paths are not symmetric. That means if we can place the detector at some position where the light paths will be symmetric for the disk frame, there should not be any Sagnac delay, because simply there will be no path difference, there will be no phase difference, because of the rotation and etc. So we just need to find out the position, placing the detector at which gives us two symmetric paths in two opposite direction, and there should not be any Sagnac delay. And that is what we are getting from the theory. We always can come up with a location of initial placement of detector for which we would not have any Sagnac delay. So it's not the rotation of the instrument. The effect is not caused by the relative motion of the emitter and the detector. And the Sagnac effect has nothing to do with the closure of the light path. Sagnac effect, as we see it, originates from the asymmetry between paths traveled by light in moving frames. So that is, but is that all? Well, for the linear case, it's easy to show, but it's not so easy when we consider the original Sagnac setup, because it is a rotating thing and we do not have access to Lorentz transformation for a rotational observer, at least not in a straightforward way. People have tried general relativistic treatment. We are working on it, but till now we have not been able to show what happens in case of original Sagnac effect when the apparatus is rotating, whether there will be a gamma factor or not. And since we cannot experimentally verify it, any gamma factor contribution only appears in the second order, and the experiment only lets us test up to the first order. We cannot have the experimental handle. We cannot cross-check our theory, but we're trying to sort of suggest what could be the possible origin, whether in case of a rotational observer, the path actually remains circular or there has to be some change. If the path is not circular, then Langevin's treatment is not working. We have to have some other treatment. So that is kind of the open issue. This is the paper we had recently, and these are some of the important references. This is the Wang papers. One was published in PRL. These were experimental determination of Sagnac effect, or the existence of Sagnac effect in the linear regime as well. This is an extensive review on Sagnac effect, sort of the to-go article if you start reading about Sagnac effect, etc. And so on. Thank you.
Questions? Yes.
I understand that practically all experiments with Sagnac effect were done with a CW light. Has it been tried with ultrashort pulses, like femtosecond pulses?
Okay, I do not know of any experiment which has been done with femtosecond pulses, but I have gone through a few literature. People are trying different ways, different kind of pulses, but till now I do not know of any experiment which uses
Yes.
pulses.
Why do you think it would make a difference?
Well, no, but it may be not difference, but at least it would give access to much more detailed study of the shift itself. Because the intensity.
But that is
light
a very interesting proposal. I'll try to figure out if there is any available literature or what improvement that can.
Yeah.
Okay, there's a question at the end.
Yeah.
Yes, I want to comment. I think it is used regularly with femtosecond pulses. That's not published because the Sagnac interferometer configuration there is not used to determine rotation effects, but just for its inherent stability, experimental stability.
Okay.
So I suppose there are.
So it's used, but not in that sense. So it's not getting published in this sense. You are saying.
Yes,
Okay.
used
Yeah.
for its
I see.
Yeah, that can be, fine. Yeah, okay. Right.
So maybe there's some room for reinterpretation.
Yeah. Yeah, okay, right.
So I have a question because it seems that in your description you assume that the frequency of light emitted in both directions is the same, but there is probably some Doppler effect. So, for example, when Czerny asked about this acceleration, it will be different if you start from stationary or moving source. So probably this is a different effect, but does it affect?
What happens in case of Sagnac effect? Yes, there are Doppler effect, but the Doppler shift does not account for the major part of the Sagnac shift. But in this case, yes, there will be a Doppler effect. But then again, the Sagnac, the main delay, what I'm talking about, will not be accounted by the Doppler effect alone. So there will be an additional effect. Yes.
Okay, Nikolai?
Okay, so in the standard treatment of the standard Sagnac effect
Yeah.
in the rotating frame, an important point which is not always emphasized is that you assume that your apparatus is addressed with respect to a Killing vector or with respect to the space-time symmetry, a kind of helical one, but it still is, and helps quite a lot in the treatment. Your extended the configurations you considered later are not of this kind.
Mm-hmm.
In the sense, the standard treatment of Sagnac effect will not work because you cannot rely on the underlying space-time symmetry. Because apart from standard time symmetry, there's also a kind of rotational.
In case of the original Sagnac effect, yes. So yeah, but the other things, the other gedankens followed because of the result Wang et al. Gave that. Okay, the notation is
Analogous to the standard Sagnac
yeah.
effect. You should be able to recover most of this time delay difference effects. Absolutely agree with that.
Yeah.
Okay.
What's the origin of this area proportionality?
Oh, okay. So when Sagnac actually proposed his formula, yeah. Okay. So Sagnac wrote down his formula in terms of A. And because all the experiments suggested the same formula, people believe that it has something to do with the area itself, even though it has nothing to do with the shape of the area. But later, after Wang's experiment and all, it has been conclusively shown that the area is just an artifact because this pi r square factor is there, but it has nothing to do with the area. In fact, in Wang's experiment, it has to do with the length. So,
We have a question online. We have a question from online.
Online question. So can you let online speakers, online channels to ask? So
Go ahead.
who has a question?
There is a
Professor,
on the screen. You have Professor Białęcki.
Professor Białęcki-Wirula. Yes, please ask your question.
I am not happy, but you're using what I might say the Newtonian law of light propagation. The way that propagates into Maxwell equations. Maxwell equations problems, but the solutions of Maxwell equations in these two different cases.
I cannot understand the question.
Maybe Professor could type the question.
Yeah.
Yes, and we can
Please type the question, we cannot hear you.
We cannot understand you.
Yeah, maybe you can type the question in the chat because the quality of the sound is very bad. We cannot understand.
Yeah.
So can you type that?
Okay, I will try to use it to write down. Okay, I'm writing down.
So I have a question.
Yeah, please.
Okay, so go ahead in the meantime.
So, have you considered the other effect, rotational effect, which is the frame dragging?
Yeah, okay.
which is an inertial.
Yeah, I understand. In this case, there is no question of trend. Yeah, there are literature which has considered trend dragging and all.
Is
All the
he
trend dragging
typing
effects
something?
are smaller.
Yeah, I
compared
think
to
he's typing
what
right.
Okay.
Yes. But I was rather, it hasn't been proven, but I was rather asking if you considered from your point of view, if you reconsider the frame dragging effect, perhaps you would have some new perspective.
Okay, so you are saying that from our point of view, when we talk about the original Sagnac effect, if we consider trend dragging.
Yes.
Yeah, but we are not at the moment thinking about GR effect, but probably that is a good idea because ultimately it's a non-inertial frame and the geometry will change. It will not be an Euclidean geometry. So probably yes.
Yeah,
but people
it
have,
happens in stationary.
Yeah, but I have seen literature where people have considered trend dragging less effect and all to explain the Sagnac effect. But then again, the contribution they get from the trend dragging, etc., are far smaller than what we can probe experimentally.
Yeah, but again, it is not what I'm asking. There is a Sagnac effect, there is a frame dragging effect,
Right.
and there is a differential frame dragging effect.
Yeah.
Which the last one has to do with the gravitational field. The last one is only physical because it involves the curvature transfer. Then there is a frame dragging which is between Sagnac, which is sort of like there are some explanations of a geometric nature. It was very nice to hear your explanation, which is very much like down to earth.
Is he typing something?
Considering the measurement part.
I cannot
But in
read.
between the two, there is this frame dragging effect.
Right. Okay.
My question is, have you tried approaching the frame
Didn't take
dragging?
my reading glasses.
No.
It's too small.
We are
Not in the context of the Sagnac, not in the context of anything else, in the context of just the
No,
frame
we have
dragging
not.
effect itself.
not yet. But that's
I would be happy to send you a review paper and hear
and definitely we can.
your feedback on that. I would be very interested to hear your.
Yeah, maybe along with my collaborators we can have a meeting also. So that
Thank
will be
you.
very
Thank you very
interesting.
much. Thank you.
I will
Okay,
read.
we
No,
have.
maybe you can project
this
it on the
question.
screen. Not read it, but project it on the screen.
No,
Can
I
we
don't know.
project
Anyway,
it on the
can you
screen?
read that loudly, this
don't know.
question, right? Because I don't have reading glasses, I see nothing.
Okay, he is asking that you are using Newtonian view of light propagation. So if you consider Maxwell's equations, that will resolve all the problem. Okay, people have actually considered Maxwell's equation and tried to prove Sagnac effect, and I have seen, although I have not extensively read that paper, but there are comments that Sagnac effect has something to do with the Berry phase and all, but we were more concerned about what happens in the rotating observer's frame or the detector's frame physically. So probably that's a very good suggestion, and there are works dealing with that, but we were more concerned with reconciling the physics, that what is behind the Sagnac effect. So we did not actually consider Maxwell's equation, but yes, there are literature and there are effects. But even then, the literature I studied, they got something out of the Maxwell's equation, but then again, the problem remains that any correction, any explanation, whatever comes up, it comes in the second order. So that ambiguity still remains because it can, Sagnac effect can only be tested up to first order. So that much I can say, but okay, I understand. Yeah, probably that is another point of view.
Okay, one question at the back.
I would like to understand better the fact that experimentally it is testable only to the first order.
Yeah, because they are only detecting the fringe shift. When they translate the fringe shift to the time delay part, etc., the sensitivity of our apparatus still today is limited, that we cannot test the second order terms in the time chilling part.
So it is not fundamental, so to say that.
No, not fundamental.
Frequency.
It's more of the technical issue. Because the noises become predominant and we cannot scale. People are trying, yeah. But it's nothing fundamentally unaccessible or something.
I would be happy to have some experimental.
Yeah, I am not very familiar with the experimental setup, but yes, I can give you some references, particularly the one paper. I'll take the email address.
More questions from the Zoom audience? No?
Can I ask one?
Yeah, sure, please.
I mean, you said you cannot actually get second order effect in the interference pattern, but is it practical reason or?
Oh, it's more practical reason. As I was saying him, since you are measuring the fringe shift, and there are some limitation of how far sensitive your apparatus can be because of the noise issues. And till now, whatever we measure, if we translate it to the time delay thing, it takes care only up to the first order. Any change in the time delay in the second order is not reflected in what we are able to comfortably measure in the fringe shift. That's the problem. We directly do not measure the time delay.
Okay, if we have no more questions, then
yeah,
there is one more.
Okay.
Yeah. Is this area proportionally can be linked to geometrical phase? Like their phase shift also is proportional to the geometry.
Yeah, but that area proportionality is not very fundamental. As I told you, that is the Wang's experiment. They did one experiment which they call zero area configuration. So practically no area was involved, only a linear thing. It turns out that it is more has to do with the length of the fiber in this case. So the area thing is not fundamental. It's better to think of it as pi r square. Don't go to that. Like, okay. Area thing is not fundamental to the Sagnac effect any longer. It's just an artifact that pi r square is there and you can write it as it.
Excuse me, I think that for this purely rotational Sagnac effect, this
Yeah.
is fundamental.
Yeah.
For this one is
yes,
and then if you add
yeah, even
discussion each other, you can cancel one Sagnac effect with the other Sagnac effect.
So you're saying that our purely rotational case, the area will be fundamental. Well, it's difficult to control. Yes, pi r square is there, and yes, for any rotational Sagnac effect, we tend to get the area thing, the formula remains. So in that way, it's correct. But okay, since we get Sagnac effects from linear regime as well, and in that case, no area is involved. So probably it's just the pi r square thing that leads to the area. There is a.
Okay, if there is no more questions, so let's end the